Alright, so in this video I want to talk to you a little bit about double replacement reactions and go over kind of examples of the different possible results of a double replacement reaction. Essentially, any double replacement reaction you find will fall under one of these four categories in terms of what the products will yield. And so I kind of want to just go through one example of each one, show you some of that. And again, these examples are from the worksheet that if you're in my class, you picked up from class. And if not, there's four examples here that you can use whether you're in my class or not. Excuse me. So first of all, probably the most common one that we think of with double replacement reactions is that we're going to get a precipitate, some sort of insoluble solid that's going to come out as a precipitate and give us a solid that we can see in the test tube or beaker where we've mixed these two solutions together. Remember, most double replacement reactions occur in solutions or mixed by mixing solutions. Not all of them, but we can basically say most of them will. So the most common result we predict is that a precipitate will form, but that doesn't always happen. That's one option. You'll have a precipitate and a soluble salt. Those are those spectator ions that don't actually show up visibly, but are there dissolved in the solution. The second possible option is that a new gas product could be formed. So where you had two solutions mixed together, now something starts to bubble off and you get a new gas that's been produced. The way to recognize this in an equation isn't necessarily by solubility, although these gases tend to be very insoluble in water. The way to recognize this is that you'll typically have two nonmetals that have combined to make a covalently bonded compound, and that's going to come out as a gas. That's not going to be a salt, because for a salt we need a metal and a nonmetal to be combined. For a gas, it tends to be two nonmetals, or perhaps a metalloid in there, but more likely to have two nonmetals combining in a covalent bond. The other product will be a soluble salt, so spectator ions, or a compound that stays dissolved you don't see. And if we look that compound up on our solubility chart or on our solubility rules, it should show up as a soluble compound. The third possible option is a neutralization reaction. This means we've combined an acid and a base, and typically a strong acid with a strong base. But the product that's going to come out of that that's unique to this is water. Water is the product of any neutralization between an acid and a base. The other second product will be, again, a soluble salt. So you should be able to look at your solubility rules and find out that the second compound is in fact something that dissolves. Technically, that's a true salt right there that we've made, and it's going to stay dissolved into water, and we've added more water, in fact, to the solution by producing this through neutralization. The final and fourth option is that nothing's going to occur. No reaction is just as important in chemistry as having a reaction, because it helps us sort out what actually has happened. When something hasn't happened, it helps us to know that the reactions we can see are actually pretty important. So having no reaction is a possible and the fourth option that we'll see here. In that case, how do I know when that's going to be the instance that we're talking about? When both of my products are soluble, they'll both stay dissolved in the water where the reaction was trying to occur, and nothing visible will have happened. We can see that in our equation, and we'll see nothing in the beaker or test tube where we mix these things together. So let's look at an example of each one. Here's one from the practice page that you'll get in class again, or if you're not in my class looking at this sheet, you can follow along with this example anyway. Silver nitrate and potassium phosphate coming together. First of all, with these, as always, remember, I want you to be thinking about the names, but also then turning those into eventually formulas. With double replacement reactions, it's really easy with names to put them together. So silver will combine with phosphate, and potassium will combine with nitrate. Now, I'm not going to write out all the names for these. I think you can handle that. I'm just going to jump ahead to the products and the reactants and products in terms of formulas. So silver nitrate will be AgNO3. Potassium phosphate, again, K3PO4. And again, we're not going to spend a lot of time with nomenclature on these because it's something that I hope by now you've mastered. If not, you need to get back and keep working on that. When these combine, silver will go with phosphate, and the order over here, which product comes first, isn't all that important. But silver will go with phosphate, and potassium will go with nitrate. Do keep in mind when you're coming up with the products, the original charges you had over here. So silver is a +1 ion, nitrate's a -1. Potassium's a +1 ion, phosphate's a -3 ion. And when those go together, they recombine with those same charges in mind. And so you need to rewrite formulas for the products over here based on those charges. So there's my rough equation. Again, I won't be working with the balancing here because I think that's something you guys can handle. So how do I know here whether this is an insoluble solid that's been produced, a gas, if I've made water, or if I've made two soluble salts? Well, let's rule out two really quickly. There's obviously not water over here, so we can rule out number 3. That hasn't happened here. Is there a gas over here? Well, a gas would mean I'd have to have two nonmetals bonded together. Clearly over here I've got metals involved. I have silver and potassium, so that's not going to be a gas. Let's get rid of that one. That leaves us two choices: silver phosphate, potassium nitrate. This is where you go to that little solubility chart or go to your list of solubility rules and look up the compounds in question. Well, if I look up my silver phosphate and my potassium nitrate, I'll find that silver phosphate is insoluble. That's a very insoluble compound. Silver tends to be rather insoluble in almost every case, except when it's with nitrate, maybe chlorate or acetate. These are very, very rare soluble salts of silver. So this one, silver phosphate, is insoluble. And potassium nitrate, I can go look it up, super soluble. Okay, potassium and nitrate both tend to be very soluble ions. So I've got an insoluble precipitate here. When I go on to complete my reaction equation, this is going to be my precipitate. Next, we'll be working with net ionic equations, and you'll start to see how these show up in our net ionic equations. But on the sheet where I'm assigning these to you in class initially, your job is to decide, are you making a solid precipitate? That's the case here. Or are you making water? Are you making a gas? Or are you making a situation where there's no reaction at all? So this is what we've got going on, a precipitate in this case. And specifically, that precipitate is here in our silver phosphate. So this is an example of how we'd look that up. Go to that solubility chart or your list of solubility rules, and you'll find that it's listed as insoluble in both those cases. Our second example, potassium iodide and H2SO4, sulfuric acid getting together. Again, let's go ahead and just finish out the products and then talk about what's happened. If I put these together, I'm going to get potassium with sulfate, and keep those charges in mind. Potassium is +1, iodide -1, hydrogen always +1, and sulfate -2. So when I make my products, potassium sulfate is going to come out the other side with those charges intact, and hydrogen with iodine, hydrogen iodide, +1, -1. Let's look and see what happened here. We didn't get water, so we'll go ahead and rule that out. Did we get a precipitate? It's possible. We'd have to go look up our solubilities on these, but let's take a look at HI here. Okay, this is two nonmetals, hydrogen and iodine, put together in what would be a covalent bond. Hydrogen, perhaps a polar covalent bond, but still definitely not an ionic bond. So hydrogen and iodine in this case are going to come out as a new gas. Hydrogen iodide gas is going to be produced here. This is a situation where hydrogen iodide is produced by the covalent bond between two nonmetals, and so there's a gas. The other product should be, according to my little guidelines here, a soluble salt. And in fact, if you go look up potassium sulfate on your solubility chart, you'll find that potassium is always soluble and sulfate is pretty soluble. And potassium sulfate specifically, sure as heck, it's soluble. So that one's going to come out the other side in solution as a soluble salt. Both of our reactants were soluble, so if we're putting those state symbols on our equation, and that's kind of part of the next layer of this work, then we would have two aqueous solutions combining to make potassium sulfate, which stays dissolved, and then recognizing that hydrogen and iodide are two nonmetals coming together as a gas, we've produced a new gas product in our hydrogen iodide, and that would go bubbling off into the room. Okay. Sometimes that's dangerous. We want to do that in a fume hood or something. In other cases, maybe the gas isn't such a big deal. Our third example, this is number 12, and we're back to words here. So again, let's skip ahead and work with this in its formula form so that we don't have to worry so much about the names here. On the sheet in class, I'd like you to write out the names. But for the sake of these examples getting a little more quickly done, we're just going to jump ahead to the formulas, assuming you can put the names together okay. So calcium hydroxide. Calcium has a +2 charge, hydroxide a -1, so we get calcium hydroxide like so. Phosphoric acid. Every acid starts with hydrogen with a +1 charge. Phosphoric means it's derived from phosphate, and phosphate is a -3 ion, which means my phosphoric acid will be H3PO4. Now, when I put these together, it's actually a little easier to see when we work with the formulas. I'm going to put these together to get calcium phosphate. So here's calcium phosphate. And I'm going to put H together with OH. Hydrogen hydroxide? Not quite. We'd never really call it that. HOH is kind of the fancy pants and almost sort of a wrong way in some cases. HOH, we want to think about that as H2O. When we put OH and H together, you get HOH. But we don't want to think of it as hydrogen hydroxide because this isn't an ionic compound. It's a covalent, polar covalent, in fact, molecule that we know as water. So H2O coming out the back of this equation. And sure enough, okay, calcium phosphate and water, obviously we've stumbled onto example of number 3. okay, where these come together in our mixture to produce water by neutralization. We've put a base, or hydroxide, calcium hydroxide, together with an acid, in this case phosphoric acid. And so this would be a new liquid, and you'd actually be producing brand new water in our reaction, okay, by neutralization. Okay. Typically, we'd expect to find a soluble salt with it. When we work with a strong acid or a strong base, that would usually be the case. In this case, we've got a strong base and a weak acid. Now, we haven't talked about those differences in class just yet. So calcium phosphate on the back of this equation, you want to check your solubility chart. Potentially, we could find that our solid, or rather our other product, comes out as insoluble. And if that's the case, you could label it as such. I'll leave that one to you to check out for yourself. But we made water by this example, and recognizing when you have that H and that OH coming together, that's what's going to happen. The final option, or the final possibility then, number 8, calcium nitrate and ammonium chloride. Again, let's skip to the formulas. Calcium nitrate is going to have formula of CaNO3,2, calcium with a +2, nitrate with a -1. Ammonium chloride, ammonium is that polyatomic ion that's positive we see as pretty much the only common one that we'll bump into. Chloride -1, so that's NH4Cl. When I put those together, again, calcium will go with chloride, so calcium with its +2 charge, chlorine with its -1 charge gives us, or chloride with its -1 charge, gives us calcium chloride as CaCl2. And our other product will be ammonium with nitrate. So NH4 with its +1 charge, and nitrate with its -1 charge. Now, when I go to look these up in my solubility table or my solubility rules, I find that nitrates are always soluble, so this nitrate will be soluble. I'll also find that ammonium chloride and calcium chloride are both soluble compounds. So when I mix a solution of calcium nitrate and a solution of ammonium chloride, these reactants together, they're going to give us, well, possibly over here, calcium chloride and ammonium nitrate, which are both soluble as well. So if I'm doing this in a test tube, mixing with another test tube or a beaker in a test tube or something like that, nothing on my product side comes out as a new thing, in fact. What we had was free calcium and free nitrate ions floating around in solution, free ammonium and free chloride ions floating around in solution, and now we've dumped those all into one container. And they all just continue to float around in solution because none of them connects with the other to form an insoluble compound. None of them forms a new gas. None of them is making water. We've got a bunch of ions that don't want to hook onto each other. Nothing, as we sometimes say in class, is a love connection here. So everything stays floating freely and loose. And you wouldn't see anything occur. When this reaction, or lack of reaction, when we combine these together, there would be no reaction at all. So how do we show that? Well, on this side of the equation, when everything stays soluble, there's nothing new being made. You had solution, solution, now you have, again, solution and solution. It's going to be really unexciting to watch, and no reaction has occurred. When that's the case, we're looking at number 4. When we're looking at number 4, and no reaction has occurred, all we're going to do is kind of forget that we even have these as our possible options. Essentially, we can just draw a line through that and say, very simply, no reaction occurs. My computer's skipping a little bit. No reaction in that case. Okay. And there's definitely going to be times when no reaction occurs. One of the next things that we'll be doing in class, depending when you watch this video, you may have already done this lab, but in lab we're going to see a number of combinations of solutions that produce no reaction. And again, you're going to find out why those are important. We don't want everything to react, because if it did, it wouldn't help us to be able to keep track of what reacts and what doesn't, and sort of separate things out and keep track and sort out the differences. If everything reacted, it would actually be a lot more complicated and not as easy as if some things react and some things don't. This is an example of when things don't react, because nothing on the product side of my equation is an insoluble precipitate, a new gas, or water, and those are all new products that we don't find here. Those previous examples show one of each. This one shows no reaction. Hopefully that'll help you out how to recognize that. Use that solubility chart and look for solubility. Watch for those new gases to be formed between covalently bonded nonmetals, but also be on the lookout for the possibility that nothing happens at all. Do your best with these. Try to work your way through the whole sheet. And when I see you next time, if you're watching this before I see you next time, we'll go through some of the answers and start taking some questions, and we'll be moving on next to net ionic equations if we haven't already done that by now. Thanks, and we'll see you then.